Audio check. Audio check. Okay, so let's get started. First of all, welcome to the Spring 2024 edition of 677 Distributed and Operating Systems. My name is Prashant Shenoy, and I'll be the instructor for this class. So what I would like to do today is first go through the syllabus for the class so you have an understanding of what this course is about, what the course policies are, and so on. And then in the remainder of the class, I'm going to give you an introduction to what distributed systems are, why they are important to study, and so on. All right. So what you see on this URL on this slide is essentially the course web page. It's also in the email I sent out to all of you, and it's also on PRs. Okay, you didn't need to write it down, but that's the place where I will post course slides and course videos and things of that sort. All right. Okay. So let's get started. And with the syllabus. Okay, so course web page I already talked about. What I'm going to describe here is also reflected in the syllabus that's on the course web page. But very briefly, the course has 3 sections. Okay, so this all of you here are in the classroom section, but there are 2 other online sections of the class. Those students are asynchronous; they're following along. Okay, I'm actually broadcasting this live for those who want to watch in real time, but also all the course videos are going to be provided, well, not just to the classroom section, but really to the online section students as well. Okay, and as far as how the course is conducted, regardless of which section you are in, you're going to do the same work. All right, same exams, same labs, same homeworks. You have access to TAs during office hours. Everything is more or less the same. Only real difference is the lectures for all of you here in this section are going to be in person. For the other 2 sections, they are recorded. And for students who are really remote, we will have office hours over Zoom. But for everybody else, the office hours will be in person. Okay? Other than that distinction, everything else is the same. As far as which section you are in shouldn't really make a difference in terms of what you should expect from this course or what we expect from you for this class. All right. Okay. So course staff. Okay. So we have number of students who are going to be helping as TAs. There are 6 TAs. Okay, one of them, Nathan, is here. Okay, you will get to know them because they are going to have office hours and so on. Okay, my own office hours are going to be on Wednesdays. Okay, right after class. Okay, so after Wednesday class, you can come and meet me in my office. They're going to be in my office, which is on this floor. Okay, but even if you cannot come on Wednesdays, there will be office hours every day. Okay, so you can go and meet somebody or the other every day of the week. Okay, and that is important when we have programming assignments and labs and so on, because you might need help. Okay, we will be here to help you. All right, so you will have daily office hours, but one day of the week will be my office hours. All right. Okay. So there'll be others who will help with grading as well. I won't put their picture here, but really you don't need to know about them. Really, you need to know who the TAs are, because they will be the ones you might be interacting with during office hours and so on. Okay. Course materials. Okay, although there is no recommended textbook for this class, okay, I will use a suggested textbook that's available for at no charge, okay, which is Tannenbaum's Distributed Systems book, 4th edition. Okay, 4th edition just came out about a year back, and that's the one we are going to use. You don't really need to buy it because the book is open source. That you can download a PDF legally for free. Okay, if you so wish, you want to go buy it, there is a inexpensive edition on Amazon. But if you are okay with the PDF version, which is what I am using as well, you can download it from the author's website. The link to do that is actually listed on the course webpage under materials. Okay, so you go there, there'll be a link. You go to that link, it takes you to the author's website, and then you can download your version from there. Okay, so keep that handy, because some of the material that I will cover here is directly taken from the textbook. So you can use the textbook as a reference, but there'll be many other lectures for which I will have other reference material. We will not necessarily have the textbook, because the textbook does not have those topics in them. Okay, but by and large, that's a good book to use for the course. And there will be course notes and other material I will make available also on the course website. Okay. So that's that. As far as the course outline is concerned, this is essentially on this slide and the next, the list of topics we are going to cover in this class. Okay, today we'll do introduction, okay, which is what are distributed systems, why must we think about them carefully when we design large software systems, basics of distributed systems, and so on. Okay, next time we'll talk about distributed systems architecture, then we'll get to inter-process communication. We'll talk about RPCs, RMIs, and so on. Your first lab will be based on inter-process communication, because you will write a client-server system for your lab. So that is going to give you the background you need for you to actually write code for your lab. Okay? And then we'll talk about processes and scheduling, process migration, code migration. We'll talk about virtualization, data centers, and so on. Okay? Naming and location management, maybe very briefly, that decided to not have too much coverage of that and add some other topics. Okay? So we'll talk about canonical problems in distributed systems, which include things like mutual exclusion, clock synchronization, GPS, and so on. Okay? And then towards the last third of the course, we'll talk about advanced topics like replication, consistency, distributed file systems, fault tolerance, security, middleware, and so on. Okay? And throughout the course, we will actually make references to many topics that are relevant to distributed systems. These include the World Wide Web, cloud computing, edge computing, sustainable computing, IoT, big data, multimedia, and so on. Okay, we might have some case studies on this towards the end of the class, but often throughout the lectures, we might make references to some of these systems as we go along. Okay? So that's in a nutshell all the topics we are going to cover in the next 24 or so lecture. Okay? All right. So let me talk a little bit about how the course is going to be graded. So we will have 2 exams for the course, one midterm and one final exam. Okay? Both of them will be closed book, closed notes exam. Okay? And that's going to be about 44% of the grade, right? And then we will have 3 programming assignments called labs. Okay, that's going to be 45% of the grade. Each was about 15%. Okay, that's really where you will learn about distributed systems. You can hear me lecture, but when you write code to instantiate those concepts in an actual system is where you really get to learn. So that's an important part of the course, which is also reflected in the grade because it has the highest overall components, 45% of the grade. Okay? And then we'll give you some assignments, which will be either homeworks, problems, or mini labs, just to give you some more hands-on exposure to whatever I talk about in the lecture. That's about 10%. Okay? And then we have 1% for class participation and participating on piazza discussion. Okay? 45% labs, 2 exams, 44%. Homeworks and mini labs is 10% and 1% for class participation. Okay. All right. As far as the prereqs are concerned, the course assumes that you know something about undergraduate operating systems. Typically, you've taken a class in undergrad operating systems, that is adequate. Okay. If you haven't taken such a class, I'm not going to ask you to not take this class, but I'm still going to assume it's your job to know something about undergrad operating systems because this course builds on that material. Okay. So if you've forgotten or haven't taken such a class, I can point you to a nice textbook that is also open source. It's the same textbook we use for undergrad OS here. Okay, that class is called 377. Okay, you can refer to that textbook. Okay, the video lectures from 377 are also available. If you want to go refer to it, that's fine too. But it's your job to know about that material because we are going to build on that in this course. It's a grad level course, so it assumes undergrad knowledge of operating systems. Okay, all right. And the second important prereq is because 45% of your grade is going to be based on programming labs. It's expected that you know how to program well in a high level language, which could be Python or Java. Okay. So if you know something, either know how to program well either in Python or Java, you should be good as far as the course is concerned. Okay, because we will start using those programming concepts to start building distributed systems very soon. Okay. Any questions on this so far? Yes.
Between the exams equal, like 20 each.
Yeah. The question is the split between the exams equal? Yes. 22% midterm, 22% final. Okay. Both closed book, closed notes. The final exam date is already on Spire. It's May 15th. That's what we are going to go with. Okay. You will see that if you log into Spire, that's what it tells you. Yes, question. Okay, question is the programming labs going to be in Java? So I was talking specifically about the programming labs. So those you can, we'll let you choose. You can pick either Python or Java. Okay, the specification will be identical. You can write your code in one of those two languages. Okay? Earlier, we used to allow you to write in whatever language you wanted, but class has become big, so we cannot service like 6 different languages. If you run into some problem, we have to figure out what's wrong. So we standardized on 2 languages. Okay, by and large, everyone knows either Python, Java, or both. So you can pick one of these 2. All right. Anything else? Okay. All right. So as far as tools, course tools are concerned, okay, we will use Piazza extensively. Okay. They will be used not only for online discussions, but also for you to ask questions. Okay, because the course is pretty large. Okay, sending email is actually not the recommended approach to get feedback. Okay, if you need to contact me or one of the TAs, use Piazza to make a private post, and we will get to it very quickly. Okay, you send me email, the email volume gets so large that emails get lost, and sometimes hard to make sure you get a timely response. So for your own benefit, I suggest that if you want to contact us, use a private post on Piazza to contact. Of course, if you have any questions whatsoever, okay, you can use Piazza to ask that question. Okay, whether you want to identify yourself or be anonymous is up to you, but this is the way we are going to essentially interact with you by and large. And then as far as public questions are concerned, everyone benefits from that discussion as well. Okay? So make sure that you use Piazza to do this. All of you should already be enrolled on Piazza. Okay? If you were enrolled as of yesterday, okay, whatever roster we got on Spire, We uploaded that to Piazza, so you already are enrolled, and we'll keep updating that if you're not yet in. Okay? So that's one. We are going to use Gradescope for assignments. Okay? Exams you will just write, but we will upload them to Gradescope. You don't need to worry about that. But Gradescope is the way we are going to use to grade everything. Okay? So that's something you will have to keep in mind. And again, we will create accounts for you. You don't need to worry. In fact, I think the accounts are already created because I linked it to Canvas. Okay, so all the accounts got populated. So your Gradescope account should already be set. Okay? And the last thing you need to know is GitHub Classroom. Okay, so you are going to essentially turn in your code to GitHub. Okay, we will basically create a classroom on GitHub. We will make sure you have an account on GitHub Classroom, and that's what you're going to use to turn in your code. Okay, so we are essentially going to use GitHub for all of the coding aspects of the course. Okay, not for homeworks and other things, but as far as coding is concerned, everything is done through GitHub. Okay, again, we will create accounts for you. You don't need to worry about it. All right, so those are 3 tools we will use extensively. Piazza for discussions, Gradescope for grading, and GitHub Classroom for all your labs and projects. All right. Course web page, I already gave you the URL. It's mentioned here. Okay, all the lectures are on our YouTube channel for the course. Okay, youtube.com/UMassOS, okay, UMass operating system. So lectures are recorded. Okay, so you can go view them afterwards. Okay, the one thing I would like to request for students in this section is to not stop coming to class because the lectures are recorded. Often easy to say, maybe I shouldn't go because I can always view the lecture later. The reason you want to come to class is to actually participate in a class discussion, because the more questions you ask, the easier it is for everyone to understand that material. If you don't come to class, there aren't enough people to come ask questions. Okay? There is no attendance for this class, so I'm not going to force you to come, but I would strongly encourage at least this section student to come regularly so you can actually ask lots of questions during lectures, make it more interactive so that not only you, but everybody else benefits from it. Okay? But the lectures are still available to you regardless. Everybody gets access to those lectures on the YouTube channel. Okay? And Canvas, we are mostly going to use that as a grade book and not otherwise, because everything else is going to be on Gradescope. So you don't really need to worry about Canvas other than to see that your grades for all the assignments are being reflected on the Canvas gradebook. That's the only reason we will use Canvas. Okay. Any questions about any of this? Yes.
Are we going to have group?
Are you going to have group assignment? Okay, that's a good question. So there are, as I said, programming projects. Okay, so those can be done in groups of 2. Okay, you can form your own group. It's not mandatory to do it in groups of 2. You can, of course, do your lab individually, but we allow that to be done in a group of 2, but not more than 2, but groups of 2. Okay, the lablets, which are really homeworks, hands-on homework, those are individual, just as any other written homework is individual. But the labs, the 45% of the grade of those 3 labs, you can do as groups of 2. Okay, so if you have somebody you want to work with, form a group, and you will be set for the semester. Okay. Any other questions? Yes. Where can you get access to the slides? Good. I'll come to that in just 1 second. So all the slides are actually posted on the course webpage. Okay, and they are posted before the lecture. Okay, and the reason that's important is one of the policies I'm going to enforce in this class is to not use a device in the class. Okay, so I'm not going to allow you to use your phone, laptop, tablet, none of that. You come to class, you just listen and participate. Okay, you don't sit on your laptop and start doing something on Facebook and then 6 people around you get distracted. Okay, so no devices of any sort in the class, which is why I'm going to post the course notes before the class. You are welcome to print them and bring them to class and take notes. Okay, so everything is on the core class web page. If you go to the web page, you will see a schedule tab. You go to the schedule tab, it will show you lecture 1. Today's lecture is already on there. Okay, so I'll post it usually on the morning of the class. Okay, so you can bring your notes with you. Okay, you can bring your laptop, but don't use your laptop in class. Okay, so no strict no device policy. It's actually better. Okay, in the end, you will actually listen more to the lecture than if you have a laptop open and are distracted and also distracting others around you. Okay, is that clear? Any other questions? That TA is the only one allowed to use the laptop because he's monitoring YouTube to make sure the stream is going through. Yes. Okay, good. So question is, how much time do we give for the lab? So first of all, the lab schedule is already set. Okay, if you go to the course web page, you will see the lab schedule. Typically by end of each month, a lab is due. Okay, there's a lab due at the end of February. I think the deadline may be either 29th Feb or March 1st. Okay, and then there's a lab due at the end of March. There's a lab due at the end of April. Okay, so I think March 1st, April 1st, and May 1st are the three deadlines for the lab. Okay, that's when it's due. But how much time do you have to do the lab? Usually it's between 2 to 3 weeks. Okay, normally around 3 weeks. I'll try to give the lab out about between 2 and 3 weeks before that deadline. Okay, so you should remember at the end of every month there is going to be a lab due. Very easy to remember. Okay, so just prepare and make sure your time allocated to finish the lab. Okay, but you will have up to 2 to 3 weeks, at least 2 weeks, but often 3 weeks to do the lab. Okay, there should be enough time. By the way, it doesn't take 2 weeks to do the lab, but we just give you more time so that you have flexibility. Anything else? Okay, so let us now switch from the syllabus. Okay, if you have other questions, feel free to ask after class. Ask on Piazza. Always happy to provide more clarifications if something is not clear. Okay, go read the syllabus, understand the policies, and so on. Okay, but now what we'll do is in the remainder of the class time, which is the next hour or so, okay, we'll talk about distributed systems. Okay, we'll talk about why they are important. Okay, say how do we define what they are, and then we'll look at a little bit of a history of distributed systems, how they arose, where we are today, how this field is evolving, and so on. Okay, so let's start with why should we think about distributed systems. First of all, most systems that you use, any computing system that you use on a day-to-day basis happens to be a distributed system. Okay, whether it's the World Wide Web, whether it's Google search engine, okay, whether it's cloud computing, if you use a P2P application, okay, all of these essentially are distributed systems. Okay, and this is also true for cluster computing, modern network computers, and so on. Okay, so it is important for us to understand, if you're interested in computing systems, to know how they work. Okay, how do you build these large systems? Some of these systems run on thousands of machines, tens of thousands of machines. How do you build one application that runs on 10,000 machines? Maybe you built applications or written code that runs on your laptop. Okay, at least in this class, you will write applications that run on 3-4 machines. Okay, but that will give you an understanding of principles that are used to build these very large-scale systems that we all are used to, whether it's social media, whether it's entertainment, whether it's search engine. They're all very large distributed systems. Okay, so it's essentially how our computing systems are built. Okay, so this course is going to try to expose you to the principles of how to build these large-scale systems. Okay, that's the first thing. Okay, now before we talk about other advantages, disadvantages of distributed systems, let's try to define this. What is a distributed system? Okay, so this slide will introduce you to several different terms that are somewhat related to one another. Okay, so let's start with something called a network system. Okay, sounds like a distributed system, but what is it? Network system is simply a collection of computers that are connected over a network that somehow communicate with one another. That's called a network system. Okay, so if you take two machines, you put it on the same Wi-Fi network, and you can communicate from one machine to the other network system. Okay, if you have a machine that or a phone that talks to a web browser, web server somewhere, that's also a network system. Okay, so that's a definition of a network system. Now, what is a distributed system, and how is that different from a network system? Okay, so a distributed system takes a network system and adds something on top of it. Okay, so a definition is given here, which says it's a network system of independent computers that appears to its user as a single logical system. Right? So what that means is you can take a network system, okay, and then you have these machines work together in some way so that they're logically connected. Maybe they just look like a single logical unit from the outside. Okay? That would be a distributed system. Okay? Simple example is Google search engine. Okay? It's a very large system. Okay? Large search engines will run on tens of thousands of machines, but your interface to it is simply a search bar. Right? So the whole system looks like a single logical system. You don't actually know what is happening behind. So it looks like a single logical system. So that's an example of how a network system has now become a distributed system. Okay? Now that's a very broad definition. Lots of different kinds of systems we encounter today will fall into that category. That includes parallel machines, that include GPU machines, all kinds of systems you might have encountered where multiple machines are connected over a network. They essentially are logically unified in some way, in some sort of single coherent system will satisfy that definition. And we kept it intentionally broad because there are lots of systems or applications that will fall into this category. Okay? Now, having defined a distributed system, let me also explain two more terms, or rather one more term, which is decentralized system. Okay? Sometimes you will hear this term as well. You have centralized system, decentralized system. So you can ask, is a decentralized system the same as a distributed system? Now, if you think about the term decentralized, it looks like, okay, it's not centralized, so it must be distributed. So it must be something like a distributed system. So the two terms are similar. Okay? A decentralized system and a distributed system are some similar concept, but if you look at how the textbook defines it, it does make a distinction between the two, and the distinction is as follows. A decentralized system is a network system, okay, where the processes and resources on that system, the applications and the resources, are necessarily spread across multiple computers, which means it's not centralized. Okay? You basically take the processes, you spread them across more than one machine. So you've gone from centralized to decentralized. Okay? But just because you make something decentralized does not also make it distributed, because to make it distributed, you need a network system where the processes and resources are sufficiently spread. It's not that you just put it on more than one machine. You actually distribute them on multiple machines with some logical intent in mind, so that maybe if some machine goes down, the rest of the system continues on. You get other properties, not just you have more than one machine that runs your application. That will make it decentralized, but to make it distributed, you want more than that. You want other properties, which I will talk about in just a second. So adding all of that properties takes a decentralized system and also makes it a distributed system. Okay? So that's the distinction you want to keep in mind. So you have a centralized system where a process runs on single machine. Okay? When you take that process resources, you spread it on more than one machine, you get a decentralized system. Okay? And then you take a decentralized system, you add other properties like replication and transparency that I'm going to talk about in just a moment, you will get a distributed system. Okay? And that is what we mean by sufficiently spread across. Okay? That's the term that the textbook uses, which is why I stuck to that. Okay? So that's the difference between these three terms. Is that clear? What we mean by a network system, decentralized system, distributed system. Yes, question. Is a decentralized system a subset of a distributed system? A decentralized is a superset of a distributed system, because not every decentralized system will be distributed, but every distributed system will be decentralized. Okay? Any other questions? Okay. So let's think about now advantages, disadvantages. I'll talk about some of the properties that distributed systems offer and so on. So why would you want to build something that is not centralized? Why not put everything on one big machine and then you have something that is relatively straightforward to implement, because distributed applications are more complex than centralized applications. What do we get by doing all of this? Okay? So first thing you're going to get is, because these machines can communicate, you can share resources. Okay? You might have multiple CPUs, you might have multiple GPUs, you might have multiple disks on these machines. Okay? A process running on one of these machines can access remote resources. It can access the storage space on another machine. Maybe it can access the processor, it can access memory, it can access GPU, and so on. Okay? So resource sharing allows these applications to become more efficient than if you couldn't share resources. Okay? That's an important advantage of making something distributed. Okay? You get better price performance ratio. Okay? If let's say you have a website that's running on one machine, okay? Centralized application. Okay? Suppose you start getting a lot of traffic on your website. Okay? What can you do because your website has become overloaded? What would you do in this case? Okay, you can add more resources. There are two ways to add more resources. You can buy bigger machine. Okay? Still centralized. Okay? You just bought more cores, more memory, and so on. Okay? And as you get as bigger and bigger, okay, the machine gets more and more expensive. Okay? So you can either add resources by making the machine bigger, or you can add more machines and replicate your website. Rather than your website running on one machine, your website can run on 2 machines or 3 machines, and requests can be split across these machines. Okay? That makes it distributed. Okay? And the argument here is that doing the latter gives you a better price performance ratios, because adding lots of smaller machines is better than buying a gigantic machine, because maybe supercomputers are more expensive than buying a cluster of machines. Okay? Or so goes the argument. Okay? So that's a price performance advantage. Okay? Now, in addition to this, you'll get several other things. You may get better reliability. Okay? Why is that? Because if you replicated that website I was just talking about on multiple machines, if one machine goes down, okay, website still available, because maybe the request can be sent to the other machine that's still running. Okay? But a centralized machine, okay, the machine crashes, the entire site is down, application goes down. Okay? So you have better reliability, because you can, if you build your application right, of course, it's not going to happen automatically. You have to add something to make sure that when machine fails, requests are sent to the other machine and so on. But if you build it right, you will get better reliability. You will get better scalability. You add more and more machines, you can service the larger and larger user base. More requests, more workload can be serviced. Your application will scale with the amount of resources you have in the system. Okay? So you get better scalability. Okay? You can also get potential for incremental growth, because when you start off with that website example, you don't need to buy a large machine or a large cluster. You can start with a small machine. As the application gets more popular, the website gets more popular, you can incrementally add resources as and when needed, rather than spending a lot of money upfront and buying a gigantic amount of servers when you don't need them. Okay? So the potential for incremental growth also makes it more economical to build systems this way. Okay? So those are all advantages of making an application or a system distributed. Okay? Now, of course, not everything comes for free. There's going to be some disadvantages as well. So there are 3 that I want to mention here. The first one is that the application becomes more complicated to write. Okay? Because the application is now split across multiple machines. Okay? You have to think about which component runs on which machine, how do they communicate, okay? Which is more complicated than writing code. You write a Java application, runs on one machine, you know how to do that. Okay? But if I say put this piece on this machine, that piece on some other machine, that's a little more complicated application to it. Okay? So the applications got more complicated, but so are operating systems and programming languages that are used to run these applications. Okay? So distribution awareness comes at a cost, which is higher complexity. Okay? So that's a disadvantage. Okay? Second disadvantage is that a network is essential, because that's part of a definition of what a distributed system is. Okay? The network is part of the system. Computers connected over a network. The entire network goes down and the system doesn't work. Okay? As opposed to if something is running on your machine, you don't have Wi-Fi connectivity, you can still run that code. So long as you're sitting in front of it, you can access it. Okay? So network connectivity is essential. Okay? In a distributed system, and that can be a problem if the network is not available for some reason. The third disadvantage is that it raises security and privacy concerns. Because your system or application is now accessible remotely, okay? Users that are not on your machine but they're anywhere on the internet could potentially access your application, access whatever the application provides. Okay? Your application is not written well, if it has bugs in it, okay, somebody can attack your application and maybe steal your data or inject malicious code and so on. So whenever you make something distributed, you're essentially making it accessible by remote users. So you got to be more careful because not every user might have good intentions. Okay? So that means that security and privacy aspects have to be considered, because that will essentially impact the system or the application you write. Okay? So these are some of the disadvantages of making an application or system distributed. Any questions here? Yeah, go. What does PL mean? PL is programming languages, OS is operating system. Okay? So it just says you need languages that allow you to write a distributed application. Of course, your OS that runs the application needs to support distributed applications as well. Okay. Any other questions here? All right. So let's talk now about these properties that I was talking about, which I said can make a decentralized system work better in many ways and make it distributed. Okay? So these properties are listed in this table, and essentially the way you want to think about this property is what is it that you are going to expose to your user, and what is it that you're going to hide from the user. Okay? So if you say something is transparent, okay, that means you're hiding it from the user, not that you're making it available. Okay? That's a definition in this case of transparency. Okay? So I'm going to start with one example, which is replication transparency. Okay? A replication transparency means that you are hiding that a resource is replicated from the user. The user doesn't know that the resource is replicated. Okay? If you have that property in your distributed application, that means that application is replication transparent. Not that the application has to be replication transparent, but if you wrote your application with and have that property be true, then your system, distributed system, is replication transparent. Okay? What's an example of replication transparent? I just mentioned the Google search engine, right? You have okay. A database that has data on more than one machine and will serve that data from the fastest one. So long as you do not expose that there are multiple databases to the user, then it's replication transfer. Okay? So let me go back to the Google search engine example. Okay? You have access to a search bar. You don't know what is happening behind the hood. Okay? That entire system is replication transfer, because the search engine there is replicated on thousands of machines, but it's not exposed to you. Okay? You don't know, you don't care, you are just accessing the system as if it is actually interacting with through a search. Okay? That's an example of replication transfer. Okay? Now, not every system might be replication transfer. You go to the Ed Lab. I don't know if you use the Ed Lab or not. Okay, that's an educational lab. You will use it for this course. Okay? You have to specifically SSH into a machine. Okay? That's not replication transparent. Although your home directory is available on all the machines, you got to access a specific one. The presence of multiple machines on the network is visible to you. Okay? That's not replication transparent. The presence of these resources is hidden from you, that will be replication transparent. Okay? That's an example of one of these properties. Okay? There are several of them. I'm not going to go through all of them. Okay? You can look at them and try to understand them, but let's take another one. Okay? Let's take location transparency. Okay? Location transparency says that where a resource is located is hidden from you. Okay? So you don't know what is the physical location of that resource. Okay? Let's take a website. Okay? www.umass.edu. Okay? Where do you think this website is located? Okay? Maybe you think the domain says UMass, so it must be here. Okay? But that domain name doesn't tell you where it's located. In fact, the website for UMass is not located here, it's somewhere in the cloud. Okay? Be that as it may, what I'm trying to say is the web is an example where the domain name does not reveal the physical location of the resource. In this case, that's the website. That is an example of location transparency. Okay? Yes, your question. Yeah, so I think that's a good question. Why is it called transparency if you're going to hide the resource? That's a technical term that's been there forever. When you say something is transparent in computer science or in at least in systems, it means you hide that from you. Okay? Although it seems like when you make it transparent, you should actually be able to see that thing. It means the opposite of what it says. Okay, but that's just a terminology that has been there for decades. So that's what we are going to go with. Yes.
I'm not talking about the location or replication, I'm about the failure property.
Mm-hmm.
Which is that the failure and recovery of a resource. Isn't the logic, inherent logic of the distributed system benefit is that if one fails, the person using it does not get to know, and he can always access a different resource.
Okay. Question is about failure transparency, and the definition of failure transparency is to hide the fact that failure has occurred and you're recovering from the failure from the user. Okay. Now, this is a good property to provide, because what does it say? It says if something fails in the system, you should not make that visible to the user. You should hide that and somehow recover from it so the user doesn't know that something is failed. Right? That is exactly what you just said. Okay? That if, let's say, you had this website example I gave, your website is running on 2 machines. Let's say one machine fails, user is trying to access the website. The fact that a machine has failed should not matter. Your system should automatically send that request to the other machine. Okay? Then you made your system failure transparent. Okay? Basically, the fact that there's a failure is hidden from the user. Transparent means hidden. Okay? So that's what it means. Okay? So in this case, the fact that there are failures are hidden, and maybe when you recover, the machine comes back on, that's also hidden. Okay? Yes. Question.
You mean when you say hidden, is it like hidden?
Hidden means not seen by the user. User does not see it.
Yeah, a person sitting in India can have a peer computer in the US, and they just send a request via the computer in the US and calculate the latency via some heuristic methods, identify where the location is eventually.
Okay. So question is, does hidden means that if some user really wants to figure something out, are they going to be prevented from doing so? That's not what we mean, right? Just because the location is hidden doesn't mean if you want to go and find out the locations by going and looking at other records and so on, that's fine. It's not like you're trying to prevent a user from figuring this out. But by and large, a normal user that's interacting with that system doesn't need to know what is going on, right? Where the location is, whether it's replicated, whether a failure occurs. You are basically saying, I will give a simpler to use abstraction or interface to user. All of that complexity is going to be hidden behind the system. So you don't need to worry about it as a user. That's what it means. If you really want to know, that's a different matter. But by and large, you should not have to worry about these things. Okay? Yes, question. Okay, question is, if the system gets overloaded and shuts down, is it failure transparent? That's your question? Okay, so question is, if you have a failure in the system, you sent all the requests to a second system, but that second system now got overloaded because getting too many requests. Is that failure transparent? That's your question, right? Yeah. So it meets the definition of failure transparency in that the fact that there was a failure is hidden from the user, but it does not give you necessarily good experience, because if you just because there's no you don't know that there's a failure, but your website is taking 30 seconds to respond and it feels really slow and sluggish, that's not a good experience. Normally, when you're saying it's transparent, it shouldn't mean that you degrade the performance of the user. Okay? So you have to design it so that it should not get overloaded. But even if it does meet the definition as written. And you did not have to deal with failure. Your requests have not stopped, okay, because you don't get an error saying server is down or something like that. It just slows down. Okay? But normally it should not slow down either. It should be designed it well. Okay, anything else here? Okay, so that's transparency. The only thing really to keep in mind is transparency here means hidden. Okay, so when you say replication transparency, you hide that is replicated and so on. Okay, so next thing we are going to talk about is open distributed systems. So when we say that a system is open, okay, what that means is, doesn't mean it's open source. It could mean that too. Okay, if a system is open, maybe the source code is available, but that's not what we necessarily mean when we say the system is open. What we mean is the interface that the system exposes to the outside world, okay, that is openly specified. So you have a known way to interact with the system. Okay? So it essentially has an API or an interface that you can use to access that system remotely. That's what we, in this case, we mean by an open distributed system. Not necessarily that the code is open. Okay? You can also make the code open and somebody can figure out how to interact with the system. But all we are asking is the interface be specified. Okay? The semantics and the syntax are sort of are via known protocols and so on. Okay? What this allows us to do is interoperability. Okay? If I know how to interact with the system, I can write other applications that work with that system. Okay? And then they work together to achieve some other goals. Okay? So you can essentially build components. The components have known interfaces. Okay? The server is a machine that's providing this. The client and the server component can be written by one company that doesn't tell you the interface. Okay? So in this case, third party cannot write another client that works with the server because you don't know how to communicate with this. But you can have client server systems that are not open. But if a server is open, anyone can write a client that works with that server because you know how to interact. Okay? That is an example of open distributed system. So it's interoperable. It can be portable because if the interface is the same, you can essentially write a new server and run it on some other machine. So long as it exposes the same interface, it works the same way. Okay? And it's extensible because of you have specified the interface, so you can extend it with new interfaces. So this is a very common way of writing distributed applications. A lot of the services you see on the web, they all expose APIs. Okay? Google Maps has a well-defined API. Okay? You can write a client that goes and essentially fetches a map for a specific location because it tells you how to send a request to make does exactly that. Okay? And the same is true for many other services. Okay? Whether it's a social media application, whether there are all these map-based applications, they all have interfaces that are specified. Okay? And in this course, you will actually see how to write these interfaces as well. Okay? That will be in lab number 2. Okay? And then you will know how to define these interfaces so that it's easy for others to essentially communicate with your application and so on. Okay? So that's open distributed systems. Okay? Now let's come back and think a little bit about centralized system, because I talked a lot about distributed systems. Let's look at the advantages of can occur. Okay? Centralized systems are not bad, by the way. They are simpler to write. Okay? If they achieve a certain task, that's a better way to write it up. But when you want to write applications that try to scale up, that serve a large number of users, centralized applications have limitations. Okay? And those are the ones that we have listed here. Think about 3 ways of centralization. Okay? You can have a centralized service, which means that there is a single server for all users, one server like a single website. Okay? You can have a centralized data, which means that all the data used by an application is on a single machine, maybe on a single disk or something like that. That's called centralized data. Okay? And you can have centralized algorithms, which means that the algorithm the application using is centralized. It runs on one machine. Okay? So these are 3 dimensions of centralization. Okay? Either the server, there's only one server, so it's centralized. The code is centralized, okay? Or the algorithm is centralized. Okay? Now you can imagine that there are, depending on where the scalability problem is, if you have any of these dimensions of centralization, you might hit a bottleneck. Okay? In case of a centralized service, I gave you the website example already. Your website running on one machine, lots of traffic comes to that website gets overloaded. Okay? That does not scale beyond a certain. There's a scalability limitation of a centralized service. Okay? The same would be true for centralized data. If you put all of your data for a single database, okay, and your remote application gets lots of queries, okay, the database gets overloaded. Centralized data will also have a scalability limitation. Okay? And the same is true of a centralized algorithm. Okay? So the centralized algorithm assumes that it knows everything about the system. Okay? And it makes decision based on some sort of knowledge about the system. Okay? And often that might also be problematic. Okay? Simple example is, let's say your website running on n machines. Okay? There is a centralized load balancer. Okay? Requests come to the load balancer. The load balancer says, I will. A very simple idea. Okay? Request come to one machine. That machine keeps track of load on all the other machines and sends each request to the least loaded machine. Okay? It's a very common approach to build website. Okay? That's a centralized load balancing algorithm. Okay? It assumes that load balancer knows about the load on all the machines. Okay? But load on all the machines is not static. It keeps changing all the time. Every time you send more requests to a certain machine, its load changes. Okay? So this centralized algorithm either has to keep checking with every machine what is the most recent load to make proper decisions, or it's going to use stale information to make decisions, which is also bad. Okay? Either there's a high overhead to collect all this information, or as soon as the information gets outdated, you are making decisions based on out of date information. Okay? Neither of which is good. Right? So you can come up with distributed versions of these algorithms and so on, which we'll look at later. But it should give you some sense of why, if your algorithm is centralized, there might also be a scalability. Okay? So whether the service is centralized, data is centralized, or the algorithm is centralized, they will all run into some scaling problem beyond a point. Until then, everything is good. It's actually the right way to do things. Okay? But beyond a point, if you want to scale to larger users, more workload, you might have to think about distributed architecture. Any questions here? Okay. So we will get to how to scale much later in this course. Okay? But here I'm going to just give you some principles. At this point, some of these may not actually make sense because you don't have enough background to understand whatever I'm going to say here. But let me say it anyway and give you some intuition at this point. And we'll come back to this much later when we talk about replication and consistency and so on. Okay? So if you want to make your application either decentralized or even better distributed, okay, you need to assume some principles. Okay? First is, no machine should assume complete information. Okay? Information should be distributed. Okay? That's called state. Okay? State is essentially information about that the application keeps track of. Okay? As far as possible, you should make decisions based on local information, not global information. Because if you need to make decisions on global information, there's more overhead in collecting the data. Decisions based on global information. It needed to know the load on all the machines. Okay? That's a high overhead to collect all that. So as far as possible, make decisions based on local information. Much better. It scales better. A single failure should not bring down the system. Okay? So if you have n machines, one machine fails, the entire system goes down. That's not a good design. Right? So you want to make sure the other n minus 1 machines can continue to function, application continues to run. Okay? So there should be a single point of failure. This is called a single point of failure. You can often write distributed application, but there's a single point of failure that can bring the system down. Right? You can have a gigantic website, but let's say the login database is kept on one machine. That database goes down, people can't log into your application. Doesn't matter whether the other machines are up or not, they can't access your app. Right? So you should not have anything that is only running on one machine. Typically, there should be a way for it to fail over to another machine. Okay? And makes the application much, much harder to write, by the way. But that is the way you write this application so that you're not going to a single point of failure. Okay? You should not assume what is called a global clock. Global clock essentially means you should not assume the machines are tightly synchronized in time. Timestamps and clock values to make all kinds of decisions in the system. Okay? but you should not assume tight synchronization, because as we will see, algorithm. All clock synchronization algorithms come with some error. So if you make any assumptions based on timestamps, often you might actually make erroneous decisions. So to the extent possible, you should not assume clock synchronization, do not assume single points of failure, you should make decisions based on local information, and you should assume that there's no global state anywhere in the system. Okay? If you follow these principles, you will essentially design your applications well. Okay? In the very first class, it's hard to appreciate what some of these things mean. Okay? But we'll come back to this as we go through the class and visit each of them in turn. And by the end of this class, you will understand exactly what those 4 things mean, right? Good distributed system. Yes, question. The question is, in a distributed system, will the load balancer be a single point of failure? If you have one machine that's a load balancer, that is a single point of failure. That is why you don't want that to happen either. Either you should replicate the load balancer or have some other machine be willing to take on that task and so on. Okay? Not every system is built that way. Okay? They will have single load balancer, but that is one point of failure. Okay, all right. So there are many different ways to build systems. We'll get to asynchronous communication, we'll get to distribution, caching, replication. All of this will help you scale your application more. Okay? The more you replicate, the more you cache, the more you distribute your data or code, and then asynchronous communication we'll get to in 2 or 3 lectures. If your communication is asynchronous, that's actually more efficient than writing synchronous communication. Okay. So with that background, the remaining, whatever, 20 minutes or so, I'm going to go into sort of a history lesson of how distributed systems evolved, okay, and where we have ended up today. Okay. So the history of this field goes back maybe 50, 60 years. Okay. So the early machines that were distributed essentially assumed what was called a mini computer model, where there was one machine and you had these things called dumb terminals that connected to that machine over a very slow network. You could essentially write your code on that machine, it would execute on the actual machine, on the terminal, it would execute on the actual machine. Okay, so essentially that did some sort of remote processing, it could fetch remote data and so on. Okay, very early form of distributed system. Now the next step immediately improved things where machines got more powerful. So you didn't have to give users low-end terminals. You could give them a workstation. Okay? Workstation had a good processor, good memory, good disk. So you could essentially now do your computation locally. Okay? But these workstations are also connected over a network. So not only could you run code on your machine, you could run code on somebody else's workstation if it was not in use, say. Right? So you could essentially take what was called a network of workstations and then use all the resources not just on your machine but on other machines. These were early forms of distributed systems, because now you could use resources on multiple machines. You could essentially have code that basically migrated from one machine to the other and so on. Okay? And we'll get to that model when we talk about processes and distributed operating system. You will see how those early systems were designed. Okay? From that arose the standard client-server model, okay, because what happened is some machines got more powerful. So then rather than having all of them being workstations that were equally powerful or equally not powerful, you had some machines that had more capacity than others. So then you had workstations and you had servers. So if you needed to run something that was compute intensive, you did it on a server. If you wanted to run something that was less compute intensive, you could run things locally. Okay? So that gave rise to client-server model, which is of course there even today. Okay? So that model is actually quite popular, is used for all kinds of things even today. Okay? But that model has evolved in many different ways. Okay? There's something called a processor pool model, which says there's not one server in the client-server model, but there's a pool of servers. Okay? And that's, we'll call that a processor pool. Okay? So it's essentially a pool of backend processors. So you can submit your jobs to the pool and some machine is going to run. Okay? So that was the next step in the evolution. So instead of, you went from many workstations to many workstations and one server, to many workstations and many servers. Okay, so that's our processor pool model, and that processor pool these days is called a cluster. Right? So you have a cluster of servers. Okay, so you can essentially submit a job to a cluster, and it'll run that job and send back the result. Okay, so large clusters are essentially run in what are called data centers, which we'll talk about. Where you can take these clusters and connect them over the net or an internet. So not if you have more workload on one cluster, it can send your job to another cluster. Okay, so the clusters themselves are connected. Now the servers are connected. Computing system, you can essentially have this. If you have large clusters in a data center that offer these services for a fee, that's called a cloud computing model. Okay, so the cluster computing model has many flavors. There's a grid computing version. There's a cloud computing version. The cluster computing model. Okay? And that is by and large where we have ended up today as far as large scale distributed story. So there's a lot more evolution of distributed system on the smaller side as well. Okay? This is the large scale system. Okay? But there are all kinds of small shape or form. Okay? So you have essentially what are called distributed pervasive systems, which basically means that technology advances have caused hardware to become so cheap that you can put a processor and a wireless radio into practically any device. Okay? And that device can now communicate with other devices. It can communicate with the network. So now everything is smart. Your toaster can actually be on the internet. Okay? Why it's not clear, but it is on the internet. Okay? But it has networking capability. So all these small nodes can communicate with one another and form what is called the Internet of Things. Okay? That's a distributed system as well. Okay? Your TV has a processor. It's a smart TV. Okay? Your car has a processor. Anything you can practically touch seems to have a processor. Okay? So all of them not only have a processor, they have communication capability. Okay? If you go back to our definition, it meets our definition of a distributed system. Okay? So not only have things evolved on the large scale, but even on the smaller side, all these devices now can do local computation, local and can communicate and so on. Okay? So computing essentially has become pervasive. Okay? That is what is meant by distributed pervasive systems. And we will, so that is some people will call it sensor networks, others will call it Internet of Things, and by and large mean the same thing. It's just small devices that are designed for specific purposes that have computing communication capability, and they can essentially communicate with other devices. Okay? So that has continued to evolve. There are lots of now domain-specific versions of this because you can have sensors to do health tracking, or Fitbit can be a smart device, and all kinds of things like that. Okay? And same with smart homes and all these other applications. Okay? So these are emerging models of distributed systems. Okay? So that's basically where things are still evolving quite a bit. Cloud computing has been around for more than a decade now, but a lot of these things are still going on in evolution. All right, so very quickly, I'm going to talk about uniprocessor operating systems and then tell you how they differ from distributed operating systems, and then we'll be done for today. Okay? So I'm assuming if you've taken a class in a undergrad operating system, you have some knowledge of what an operating system is. Okay? So the operating system is basically the piece of software that runs on top of your hardware on your machine and gives the user and the user's application easier to use abstractions. Essentially, it's an arbiter of resources. It gives logical abstraction. So for example, your operating system gives you a file system abstraction. So you can create data and store them in files, but as a user, you don't need to know where on the disk that file is. Okay? That's the operating system's job to figure out which specific location to put that. Similarly, you can start new application. You can start a browser, you can start a word processor. Okay? But you as a user don't need to worry about how much memory should be allocated to this application when it's executing. Okay? Should it be given 1 megabyte, 10 megabyte? You don't need to worry about it. You just start your application, you do your work, the OS takes care of that for you. Okay? You don't need to worry about if there are 10 applications running all at once, how should the hardware be allocated, how much time should be given to this application versus this other application. Okay, the OS is going to take care of that for you. Okay? So in some sense, a lot of the underlying hardware features are again hidden from the user by the OS. Similar to how distributed systems hide lots of complexity, the OS is also hiding a lot of complexity. Because otherwise the machine would be very hard to use. Every time you created a file, you have to go to disk to find an empty location, say put it there. Okay? That's just something you don't have to do. OS will do it for you. Okay? So giving an interface that is much easier to use than actually using the hardware directly. Okay? So that's what a job of the OS is. Okay? Now, again, just as distributed systems have evolved, so have operating systems. Okay? The early operating systems were written as a single blob of code, which were called monolithic operating systems or monolithic kernels. The kernel is the part of the OS that actually is the thing that boots up when you start the machine. Okay? So monolithic OS means essentially the entire OS is like one program, like a central, think of it like a centralized application. So it's just one thing that boots up, and that's your monolithic. Okay? Now, as operating system began to get more and more functionality, writing OSs as a monolithic piece of code did not scale very well. But then each OS developer had to know about every single part of more modular. Okay? So operating systems evolved in many ways, okay? And so there were many different ways to make this modular. One is called the layer design, okay? Where the functionality is decomposed into n layers. Okay? Each layer can talk to the layer above and below it. Okay? So layer I can only talk to layer I plus 1 and layer I minus 1. Okay? The network protocol stack, which is part of the OS, is written in a layered fashion. Okay? TCP/IP, if you know something about TCP/IP or the OSI protocol stack, that's a layered design. Okay? If you don't know about it, don't worry about it. Okay? Just you need to know what layered design is. You don't need to know what network protocols are for now. Okay? So that's one approach. Okay? Another approach was to design what was called a microkernel architecture, where you said rather than making the OS very large, let's make the kernel very small. We'll call it a microkernel. Okay? That's the part that will boot up. Okay? And whatever you typically put inside the OS, we will actually run it as a user process. Right? So typically, file system is part of the OS. In a microkernel architecture, the file system runs as an application process. Just as your browser runs as an application process, your file system will run as application process. Memory manager will run as application process. Process manager will run as an application process. Okay? Typically, they are all part of the OS and they're sitting inside the OS kernel. Here in a microkernel architecture, you made them components that run as independent processes, and all that the microkernel is doing is allowing these to communicate and do their job. Okay? So the microkernel provides a very fast intercommunication framework, inter-process communication framework. Okay? So this is a different way of writing your OS, where each component is written as a separate application. Okay? From a software engineering perspective, this is a great way to write your application, because you want to modify the file system, you just need to worry about that application. You don't care about all those other ones. They're exposing good interfaces that you know about. That's how you communicate with them. But beyond knowing the interfaces, you don't need to know what's inside it. Unlike in the monolithic case, you needed to know lots of things. Here you don't. Okay? So this was a new way to design operating systems. And there were several research projects that did this. Early versions of Windows and Mac OS actually used this architecture. Yes, that was 20 years ago. Okay? But the architecture actually never became completely successful because it had one limitation. Okay? And you think of what that might be. It's slow performance. Why is it slow? Okay. The performance. So this is a really nice way to write a modular system, but also it has an impact on performance, because if the let's say the process manager needs to start a new process, it has to send a message to the memory manager saying, give me 10 megabytes of RAM for my new process. Okay? So that's a message that has to go from this application down to the kernel back to this application. Okay? So now the claim is that is slow, because if everything was a monolithic piece of code, Okay, you would just make a function call because all of this is within the same process. So this component of your code just makes a function call to that component. So what was a function call has now become an explicit message that has to go from one process to the other. That significantly slows down performance. Okay? The function call is much faster than sending a message from one process to the other. Okay? So this had a significant impact on user performance. Feels that the machine is slow, then you got to do something, right? So as you cannot say this is the way it is going to be. So a lot of the monolithic architecture pieces started moving back into the kernel. It's slow, so this part is sending too many messages, put it back into the kernel so that it can interact faster. So you've gone from monolithic architecture to microkernel architecture back to an architecture where the code is all inside the kernel, but except for one difference, which is that you made it modular. Okay? These components that were processes essentially became modules inside the kernel. So you still had that software engineering advantage, saying here's a module that's self-contained. It has well-defined interfaces. You communicate through the interfaces. It's part of the code, but you can essentially treat it as somewhat independent. Okay? So that's how today's operating systems are. They use a modular architecture. They don't necessarily use a microkernel architecture. Okay? That gives you some of the software engineering benefits, but also gives you performance advantages. Okay? Now, there's a disadvantage of putting everything back in the kernel, which is security. Okay? One advantage, big advantage of microkernel architecture was it had better security properties because if there's a bug in the file system module, you could probably attack it, but then you cannot actually attack other pieces of the kernel. As opposed to monolithic architecture, you essentially attack the kernel, you take over the entire OS. Okay, that's game over. Right? So here you have better advantages, which modular or monolithic systems will not give from a security perspective. Okay? There's a nice article on this that's a suggested reading between Linus Torvald, who started Linux, and Andrew Tannenbaum, who was promoting microkernel architecture, as to what some advantages and disadvantages of these two architecture. So you can go and read it if you're interested, but a basic thing I already mentioned here. Okay? So very quickly, before I end, I want to tell you how distributed operating system is different from all of them. Everything I talked about so far still runs on one machine, not distributed, whether it's microkernel, whether it's monolithic, modular, single machine. Right? So still, so what a distributed operating system does is it takes the kernels on multiple machines and makes this entire set of machines look like one logical machine to the end user. Okay? There may be 10 machines, but when you interact with them, it just looks like one logical big machine. Okay? That is essentially what a distributed operating system is. And you will see now in doing so, it's hiding lots of things. Okay? It's providing lots of types of transparency. Okay? You are getting replication transparency. You don't know there are 10 machines. You might get migration transparency. You are start running a process on machine 1, then it may move it to machine 2. You just see the application is continuing to run. You don't know which machine it's running. It just looks like it's running the application and so on. So there are all kinds of good properties that come with it. Okay? That is a distributed actually an example. Here is an example of operating system. Independent, let's say this is Windows or Mac or Linux. Okay, that's a Linux. Okay, and then you put a layer on top of it, which is a distributed operating system service. Above this layer, these applications just see one logical machine. Okay. So something it does, you don't know whether it's running here, here, or here. So that's taken care of by this distributed operating system. Okay? So you get this logical abstraction. That's a distributed operating system. Now, if you didn't have this layer, okay, you are running application on this, you get what is called a network operating system. That's just your regular Linux or Mac. You just have a machine that has connection to a network. That's called a network operating system. Just that the machines are connected. Okay, you can essentially explicitly log on to another machine and start network OS. But if you have this layer, you can just start an application. The OS takes care of deciding where it runs and so on. Okay? So that's the difference between a distributed and a network operating system. Today, every OS is almost guaranteed to have be a network OS because it has communication capability. But most of them don't have this feature. Okay, that makes it distributed. Okay, so that's your network OS, okay, where the presence of these things are. Sorry, no, that's a network OS where the presence of these machines are visible to the application. You're not hiding them. Okay, now if you can take a network OS and write a piece of top of it called middleware, which will take a network OS and try to hide some features of the machines underneath. So you're trying to emulate what the distributed operating system would do using an application level layer. It's not an OS layer. That we'll call a middleware service. Okay? The middleware service takes a standard, whether it's Windows or Mac or Linux, adds some layer, and then starts hiding some. So it's easier to use. Because most applications are standard machines that are not running a distributed. Okay? So keep these three concepts in mind. We started with the monolithic kernel, so single machine operating system. And then we said you can connect those machines together. You get a network OS. That's every OS you have today actually is that. Okay? And then if you run a layer on top that hides the presence of the machine, that's a distributed OS. Okay? Or if you as a user, a developer write this layer as opposed to OS designer, so it's not an OS component anymore. It's an application level layer. Then you get a middleware service that is trying to give you something similar. That's called a middleware OS. Okay? So there are these 3 or 4 concepts rather that you need to know. I'm going to end here. I'm not going to go through this table, but you can go and understand the differences between a distributed network and a middleware-based operating system in terms of what it exposes, what it hides, what kinds of advantages it has. Okay. All right. We'll end it here today, and I will continue with the next topic, which is going to be distributed systems architectures on Wednesday. Okay. All right. Thanks.